Hello everyone, welcome to this new session on switching theory and logic design. Myself Dr. Sohail Rana, and this is part 3 of minimization of switching functions. In previous two parts we have seen various variable types of K-maps. Today we will extend our discussion about K-maps. So basically, if we want to define K-map, that is short form of Karnoff map, that is K-map. It can be defined as it is a chart or a graph composed of an arrangement of adjacent cells, each representing a particular combination of variables in sum or product form. So either we may have some possible SOPs, 2 to the power n possible combination of product term, or 2 to the n power possible combinations of POS form. So suppose if K-map, if we are having some 2 variable, for 2 variable K-map, say we will have maximum value of 2 to the power 4. So we can have, say, 4 cells or squares, right? Now if we talk about, say, 3 variable, so we can have 2 to the power 3, that is 8 cells or squares. Similarly, if we talk about 4 variable, we can have 2 to the power 4, that is 16 cells or 15 squares, and so on. So any Boolean expression can be expressed in a standard or canonical or expanded sum of product, that is nothing but AND form, or in a standard or canonical or expanded POS form, that is nothing but OR form. So we can represent them, and each of the product term in the standard SOP is called a min term, and if we convert it into POS form, it is max term. So for simplicity, min terms and max terms are usually represented as binary words in the form of, say, zeros and ones. So min terms we represent by small m, max terms we represent by capital M. So let us now see some examples about 2 variable K-map. So let us consider a 2 variable K-map. So 2 variable expression can have 2 to the power 2, that is 4 possible combinations. So we can have 2 input variables, say A and B. These 2 will consider as our inputs. Now each of these combinations we can write in SOP form. As SOP form we can write them as, say, A bar, B bar, or A bar B, or AB bar, or AB. So it will be called as, say, min term. Say that is nothing but 0 0 0 1 1 0 1 1. So when we write it in this form, we term it as min term. Now if we do the opposite, we get the max term. So suppose if we consider some expression, if some expression is given, say function f is equal to a bar b bar plus ab bar plus ab. So this we can write in the form of min terms as, say, f is equal to, now this is a bar b bar, so this is first term we represent as m0, this is m1, m2 and m3. So here we have m0, then ab bar is m2 and ab is m3. So like this we can write them. So in tabular form, if we represent the same thing, we can draw it like this, say min term, and we have, say, inputs. We have two inputs, A and B, and we may have some output, say F. So min term maybe, say, 0, 1, 2, 3. For this 0, inputs will be 0, 0. For this 0, 1, and this is representing 1, 0. This is representing 1, 1. So there may be some output of our expression, say 1, 0, 1, 1. So like this we can have the different values in table. Now we have seen how to make the mapping of SOP expression. Say mapping we can do by simple 2 by 2 matrix, because as per 2 to the power 2 formula we can have 4 squares. These 4 squares will represent the 2 variable K-map table. So we have 2 variables, this side say we'll keep A, this side it will be B. This will represent 0, 1, 0, 1. So inside, if we write them in terms of A and B, first one will be, say, A bar B bar, second one will be A bar B, third one will be A B bar, fourth one will be A B. So this is like 0, 1, 2, 3. Now how to minimize the SOP function? Now to minimize these functions, if it is given in the SOP form by using K-map, we have to look for the adjacent squares having ones. That is min terms adjacent to each other, and combine them to form larger squares to eliminate some variables. Two squares are said to be adjacent to each other if their min term differ in only one variable. For example, in two variable K-map, say M0 and M1, say this is M0, this is M1, this is M2, this is M3. Say M0 and M1, that is A bar, B bar and A bar B differ only in one variable, that is B. A is common, only B is changing. So they can be combined to form a 2 square to element the variable B. Similarly, suppose any other adjacent to each other terms are there, we can reduce them. So the possible minterm grouping we can form, suppose if we combine m0 and m1. Say we have some function, for example, say we have one function f is equal to m0 plus m1. That means these values are high, 1. So in the square 2 by 2, we have this as m0, m1, m2, m3. This side we have a, this side we have b. So m0 plus m1 means here we have 1, here we have 1, this one is 0, this one is 0. So what we can do, the adjacent ones we can make a square, we can select them. So we will select these two, right? So for this, what is the expression? m0 is a bar b bar plus m1 is a bar b. So here we can take a bar common, so here we can get b plus b1. So this one we can eliminate as 1. So here we get only a bar. So this function is representing a bar. So here we have a bar, b bar, a bar b. So only a bar will be existing. So this is 0 1, this is 0 1. Similarly, if we have some other expression, say other function, for example, say this is function 1, here we'll give 2. Say f2 is equal to m0 plus m2. So for this we can have these 4 squares. This side we have a, this is b, 0 1, 0 1. So this is 0 1 2 3. There we are saying m0 and m2. So m0 is here, so it will be 1. Here m2 is here, so it will be 1. Remaining will be 0. So we will make a pair of these two. Now for these two, the common term we will find out. So here m0 plus m2 is a bar b bar plus say ab bar. So here b bar is common. Here we can write a plus a bar. So this term we can eliminate. So remaining will be b bar. So here in this box a is 0, b is 0, here a is 1, b is 0. Then similarly we can see, say for third possible condition also we can take, say we have one function f3, it is given as m1 plus m3. We can write it as say a bar b plus ab. So here b is common, we can take b common. Here we will get a plus a bar, the remaining will be b. Similarly, we can have various combinations, and for this if we draw the 4 squares, then we can mark ones. Here it is 1 and this is 3. 1 2 3. 0 1 2 3. Remaining 2 will be 0. So we have to make combination of these two. This is A, this is B. So these two squares adjacent to each other can be combined to form a 4 square. A 4 square eliminates 2 variables. A 4 square is called a quad. 4 square is called as a quad. So to read the square on the map after minimization, we can consider only those variables which remain constant throughout the square and ignore the variable which are varying. Then we can write the non-complemented variable if the variable is remaining constant as a 1. Okay, so like this we can read. Like f1 is read as, say here we have solved f1. This f1 f1 is read as a bar because along this square a remains constant as 0. So here also a is 0, here also a is 0. Both the places a is equal to 0. But along this square b is 0 and b is 1, changing. Right? So it's constant 0. 0 stands for bar. So this is a bar. Now if we focus on this function 2, m0 and m1. Now this is m0 and m1. You can see which value is constant here. b is 0 throughout this complete square. And that value is 0, that's why we are writing b bar. And a values are changing, so that value is eliminated. Similarly, if you observe here, which value is constant? Here this belongs to b. So b is 1, both the places constant. 1 represents direct b, not b bar. But on these two places a value is changing. A value is changing for these places. So this will be b. Now if we get, suppose, another function, say f4 function, where we take say m0 plus m1 plus m2 plus m3. So there all the boxes will cover the ones. 1, 1, 1, 1. So here we can make a square box of 4. All 4 will be combined. So here we have A, here we have B, 0, 1, 0, 1. So on these squares, how fi will be read? No variable remains constant throughout the square, which means that the output is a 1 for any combination of inputs. So its answer should be 1. So say if we solve for this, m0 is, say, a bar b bar plus a bar b plus ab bar plus ab. So here we will take a bar common, b plus b bar eliminated, plus a common. So here b plus b bar eliminated. So here we will get a bar plus a, that is nothing but 1. So this will yield a 1. So like this we can solve the two variable K-map. So with this we will stop this session here. Next session we will continue our discussion on K-maps. Till then, have a good day. Thank you.